In my game Moose Miners, there are trillions of gems that can be mined. The gems are placed in a grid that is about 32,000 tiles wide and about 2 billion tiles deep. Each tile has a gem on it, which means there are about 64 trillion gems that can be mined in total on the map. With the current upgrades I have in the game, no one would be able to mine deep enough to mine all of the gems. But it is nice to have that huge limit to have the option to add some ridiculous upgrades that lets the moose mine really fast. So how do you make something of this scale work without running out of memory and keeping a playable framerate? The problem can be divided into two parts, the logic part and the rendering part. Let's start with the logic part. The logic is responsible for storing which gems are on the map and which have been mined, as well as making it possible for the moose to find and mine the gems. I like to work in a data-oriented way when solving problems, and with a problem like this, it is extra important to solve from a data perspective, since 64 trillion gems can easily become too much data to even store on a typical hard drive. Just storing 1 byte per gem on the map would result in 64 terabytes of data to store. That would not fit on any consumer hard drive and certainly not in RAM. And there is more data than would fit in a single byte that is needed for each gem. Each gem needs a position on the grid, a gem type, how many mineable pieces that are left in the gem to mine, what color the gem should have, how much health the gem has left before it breaks, how hard the gem is to break, and possibly some more stats. Just storing these for each gem would result in maybe around 20 bytes if stored reasonably compact. It could be reduced a bit by doing some tricks in packing perhaps. Still, it would be much more than the already too much 64 terabytes of storage. There is no way we fit that amount of data in a game. The solution is to rethink the way we store the gems completely and maybe make some compromises in the possible gameplay the game can have as well, to make this very large map work. So instead of storing data for each gem, I just store how many gems that have been mined so far for each column in the grid. This means that I can reduce the data from 64 trillion instances of some gem struct or similar to just an array of 32-bit integers that are about 32,000 long, which takes about 128 kilobytes. Quite the difference. But with this solution comes some issues and limitations. Just storing how many gems have been mined in each column does not cover all the data as said was needed before. Just which gems are left on the map and which are not. So we need some more arrays to cover the other things. There is another int array for the gem health that stores how much health is left in the most southern gem in the column, as well as another int array that stores how many pieces are left to mine. Now let's think about the gem types. If, instead of just defaulting to storing the type for each gem, we think about the data that is actually needed, we can optimize it a lot. For the gem types, I want the gems to be more valuable the deeper into the mine you get. So by just deciding to have the types appear after each other 25 gems at a time, we can just write the function that takes a grid position and returns the gem type. Then I also wanted some more rare gems that are spread around here and there in the mine. Gold, diamond and black gem. These I just placed procedurally by extending the getGemType function. By passing a seed that is based on the position to a pseudo-random function, we can make sure that the rare gems always appear in the same spots as long as the same seed is used. Now, with this new way of storing the gems come some technical limitations that are going to affect the gameplay design possible. The main one being that only the gem most south in the column can be mined, so it is not possible to mine horizontally through any columns. That is a limitation I am fine with in order to allow a very large map and a very large base. And since you cannot directly control the miners, it is easy to uphold this limitation by just having the miners only try to mine gems that actually can be mined. Having a player-controlled character in the game would make this much trickier, and at the very start of development of this game I played with the idea of having a player-controlled character as well, that you could upgrade. But I decided to only have AI-controlled characters to easier support this way of storing the gems. Now, let's have a look at the other big part of the problem of a very large map, the rendering. There are a lot of different ways to tackle rendering, and I have gone through some different options during development. The first one is the draw model and draw mesh functions that come with Raylib. It is the most naive version, resulting in one full draw call for each thing you draw, and sets up matrices and textures for the model every time you call it, whether it's needed or not. The big benefit of this is that it is very convenient to use, as you just call it with the model you have loaded and then it just works. The bad thing is that the performance is terrible if you want to draw a lot of things. At the start of development I used this for everything just to get things going. At that time I just used simple blocks for all the graphics, so it was not too expensive, and the scale of the game besides the gems wasn't that large yet. I still use this to render the portals of the storage rail, since that is just 2 objects, so there's not much overhead that can be saved on those anyways. The next version is 2 sets of functions that are made based on a few Raylib functions, called draw meshes with same material and draw same mesh with same material. It comes with 2 different setup functions called begin draw meshes with same material and begin draw same mesh. Begin draw meshes with same material sets all the uniforms needed in the shader for a material, and begin draw same mesh pushes the vertex data of a mesh to the GPU. Then, when one or both of these are called, you can just call draw meshes with same material or draw same mesh with same material to render mesh. This makes the draw calls much cheaper when rendering multiple instances of the same mesh or rendering multiple meshes that use the same material in sequence. Using this method brings down the overhead when rendering multiple meshes quite a lot compared to using Raylib's draw model or draw mesh. And these functions were really easy and quick to set up due to Raylib's very straightforward and easy to understand code. I used these for a few of the models in the game, the ones that need to be rendered in multiple instances but not that many instances, such as the storage minecarts and its rail. Now, some things in the game need to be rendered in very large numbers, such as the gems and the moves. For this, it is worth doing even better batching by using the draw instance draw calls available in OpenGL. Raylib has an example of this with their own draw mesh instant function. This one works quite well and is a rather direct way of using the instance drawing of OpenGL. I did, however, make my own version of it since there was one big problem with it. In order for it to be simple to use, the draw mesh instance function takes an array of matrix structs, which is what Raylib uses for transforms on the CPU side. But in order to be sent to the GPU, it needs to be translated to a float 16 struct. So the draw mesh instance function solves this by allocating a float 16 array and translating and copying the data from the matrix array to it. This is a big no-no. I want as few memory allocations when the game is running as possible, and certainly no allocations that happen every frame. So I made my own version of this function that is almost identical, but instead of taking a matrix array, it takes a float 16 array directly, which lets me skip the allocation and copying altogether. So instead, when I set up the transforms for the instances, I just store them directly as a float 16 array. Using instance rendering makes the rendering much faster for the meshes that are rendered with a lot of instances. But for the gems, there is a problem. The different gem types need different colors. And the draw mesh instance function only has support for unique transforms for each instance. So I made an extended version of it that also takes a color array to pass a color for each gem. This worked quite well, and now we can render quite a lot of gems without the frame rate dropping too low. But we could do better. Passing data from the CPU to the GPU is expensive, so we want to send as little as possible. It would be better if we could avoid having to send the color of the gems to the GPU. This becomes even more relevant when looking at rendering the gems in the miners' carts. There can be quite a lot of miners on the screen at once, and after some upgrades they can carry a large amount of gems, resulting in hundreds of thousands mined gems to be rendered. To solve this, we should go back to thinking data-oriented again. What is the color data of the gems really? How dense it is, for example? It's not really dense at all. There's a lot of repetition in it, since the total colors of the gems are quite few, and most of the gems that are visible on the screen at once are going to be of the same color. So, when looking at it like that, it is really inefficient and rather stupid to send the color value for each gem to the GPU. Instead, we can split the rendering of the gems into several render passes, one for each color. Then we can just set up the color of the material once per render pass and skip sending the color for each gem completely. So this is what I did for the mine gems. I have this instant render pass struct that describes the render pass for the gems, and then I just have an array of these with one entry for each gem color. Then, when preparing the transforms of all the gems, I just select the render pass entry in the array that corresponds to the color of the gem and add it there. Rendering these is then really simple. Just loop through all the gem types and get the color for the type to set that to the material, and then call the draw meshed instance that does not take a color array, and we are done. This solution also reduces the memory footprint by a lot as well. Instead of needing a color value for each instance of gem that should be rendered, we only need to store a single instance render path struct per color. That was all for this devlog. If you liked it and want to see more like this, please wishlist Moose Miners on Steam. It will help me keep making videos like this. And tell me in the comments what other parts in the game you would be interested in how I solved. Thanks for watching. Bye!